Today we are going to cover the topic of regular expressions and deterministic finite automata. This is an important topic which we have sort of seen in our initial lectures when we built the lexer component of the interpreters and compilers which we have seen. In particular, the PLY system employs regular expressions in the lexer specification. Okay? So today we are going to deep dive into regular expressions, and in particular deep dive into the topic of how the PLY lexer system handles these expressions and what it does with it and how does it generate the tokens. Okay? So this is a topic behind the scenes, what happens in the PLY lexer system or the automated compiler generator systems like PLY. All right, so this is going to be a little bit theoretical, but also we're going to study the algorithm, the main algorithm which is used by these compiler systems. Okay. All right, so let's get started. I think most of you have a vague idea or maybe a good idea of regular expressions, but we are going to give it a more mathematical treatment right now. Okay. So here's a definition of actually some definitions, not just one definition. We start off by defining what a language is. Okay, a language is a set of strings, okay, made up of symbols from an alphabet. Okay, so we are given an alphabet. We call it sigma, a Greek symbol sigma, and these are symbols. Typically, this will be the symbols on your keyboard, the ABC, 1, 2, 3, plus, minus, all those symbols you see on the keyboard. Typically, that's what it'll include. But for our mathematical treatment, we'll go with a simple two letters alphabet, A and B. Okay, all the examples in this set of slides will use A and B as the two symbols, just the two symbols. Okay. All we study here is even with the example of two symbols will apply to any number of symbols. So it's not losing any generality here. Okay, so we define a language as a set of strings, okay, and made up of symbols from the alphabet. And here are three examples. L1, we are going to assume the alphabet sigma equals A comma B. So all the languages we are defining will use that alphabet. So the first one is L1, which has only 4 strings in it. 1, 2, 3, and 4. Okay, so it's a finite language. This particular L1 is a finite language. It's made up of 4 random strings. I just picked randomly. Okay, so you can actually create other languages which are finite, okay, by just randomly picking strings you like and put them into a language and say that that's my language. Okay, that's a finite language. Now, finite languages are of not much interest to us. Okay, in computer science, we are more interested in infinite languages which follow certain patterns. So here are a couple of examples. L2 is a language of again strings made up of A's and B's. And the property each string has is that each string has equal number of A's and B's in it. Okay, that is certainly not true for L1, right? Because you can see the first string is AAB and it's got 2 A's and 1 B. So that does not have equal number of A's and B's. Okay, but you can make words or strings made up of A's and B's in which there are equal number of A's and B's. And I listed 4 of them here, but I also put the ... to indicate that there are many more. Okay, and actually there are infinite number of these. Okay, so you can see the first one is AB, which has got 2 A's and 2 B's. The second one has got 3 A's and 3 B's arranged in a certain manner. And the fourth one has got 2 A's and 2 B's arranged differently than the first one. The lambda is the symbol we use to denote the empty string. Usually in Python or other languages, we put the two double quotes next to each other. But here, we will, in math or mathematical treatment of regular expressions and languages, we will use the lambda. Okay, so lambda also belongs in L2 because lambda has got 0 A's and 0 B's. Okay, so and so on. So this is an infinite language. A third language, L3, is again W, such that W is made up of only A's. Now this time we don't allow B's in the strings of L3. Okay. But the additional condition is that the length of the word W or the string, we sometimes refer to W as a word, okay? But strings and words are interchangeably used. The length of W is said to be prime in this language, okay? So obviously you need to know what a prime number is, and let's say that 5 is we know that 5 is a prime number, so you can put 5 A's together and say, oh, that belongs in L3 because it satisfies this condition, okay? But again, this is infinite because we know that there are infinite number of primes, okay? So that's what a language is, okay? So language is a set of strings, finite or infinite, made up of symbols from each string is made up of symbols from the alphabet which is given to us. In our examples, it's going to be A and B, but you can have other symbols in other examples. Okay. Now we also studied 3 important operations on these languages. So now these languages are sets, right? So set here we said that a language is a set. So we define 3 set operations on languages. Okay. Languages means sets of strings. One is called the concat or product, okay? The second is called the union, and the third is called the star operator, okay? So there are 3 operations on languages. Let's look at each of these in turn. L1 dot L2 is a product of L1 and L2. It is the set of strings W1 dot W2. Now W1 dot W2 I have explained here is a concatenation of 2 strings. Okay, when you take 2 strings and put them together one after the other, you get a longer string, and that's what this W1 dot W2 is. Okay, so this is a concatenation here. Okay, so but what are W1 and W2? W1 must come from L1 and W2 must come from L2. Okay, and if you pick a word from or a string or a word from L1 and a word from L2 and put them next to each other and make a bigger string, then that string belongs in L1 product L2. Okay. Now this must be done for all possible values for W1 and W2. Okay. So this can, of course, if L1 and L2 both are finite, then L1 dot L2 is also finite. But if of course even one of them is infinite, the product will be infinite. Okay. So that's called the concatenation of 2 languages. The next one is the union, pretty standard definition of union of sets. L1 union L2. Okay. L1 union L2 is the standard definition of set union. Okay. W such that W belongs L1 or W belongs to L2. It's called the union. Okay. So union and product. Okay. And the third one is called the star operator, L star. And it is based on the definition of the product. But we are given only one language L, so this is a unary operator, whereas L1 dot L2, the dot there is a binary and union is a binary. Okay, but the star is a unary operator. You can apply it to any language L. Okay, and what it is that it is the union, infinite union. Okay, so it's an infinite union of the languages which are formed by taking the product of L with itself any number of times. Okay, so for example, L dot L, that is 2 L's and then a product of L with L itself. Okay, L dot L is 3 L's and then there's a product L dot. First take the product of L and L, and then the result of it take a product with another L. Okay, so this keeps on going. It also includes the case where there's only one L. Okay. Which is basically L itself, and also includes when there is no L's. In that case, what we do is the definition includes the empty string there. Okay, so the empty string is always a part of the L star language. Okay, but then L star includes many more. It actually includes all the strings from L, all the strings from L dot L, all the strings from L dot L dot L, and so on. Okay, it's an infinite union. Okay, L star. Another way to think of L star is, given L, which is a set of words or strings, the way you make up words in L star is you take any number of strings from L, any number, okay? It's your choice, any number of strings from L, and string them all together, you get a word or a string in L star, okay? So any number, okay, and also you can repeat the same thing, okay. So any number of strings from L, you can take the same string from L and repeat it 4 or 5 times if you want, and another string and repeat that 3 times, whatever it is. So you can take any number of strings, any number of times, and string them all together, and you get a string in L star, okay. So this is called the star operator. It allows you to combine words from a language any number of times to make a bigger language, a bigger word in the L star language, okay. So those 3 operators we will consider when we study regular expressions, okay. So that's all there is as far as languages are concerned. So language, let's recap. A language is, given an alphabet, a language is a set of strings from that alphabet, okay? It could be finite or infinite. And we define 3 operations: the product of 2 languages, L1 dot L2, the union of 2 languages, L1 union L2, and the star operator on a language, L star. All right, so now we come to the main topic, which is the regular expressions, okay? And we have seen in the lecture specifications in the previous classes and assignments, we have written some rudimentary regular expressions for tokens, right? And the topic is exactly the same here, okay? Except that we have a more formal treatment, a little bit more mathematical treatment of this topic, okay? All right, so what is a regular expression? It's a mathematical mechanism to define a class of languages called regular languages. Okay, so it's a mathematical mechanism, which allows you to define a language, and in particular, those languages have certain properties, and they're called regular languages. Okay, all right. And here's a definition of a regular expression. Again, it's a limited definition, mathematical definition. We might have used more than what is available in this definition in our lecture specification, but those are all variations of what we are studying here, okay? All right, so there are 3 parts to a regular expression definition. One is that any symbol in the alphabet automatically becomes a regular expression, okay? So for example, A by itself is a regular expression. Even though it's a symbol in the language, it's also a regular expression, okay? B is also a regular expression. Okay? So every symbol in sigma becomes a regular expression. Then there's a special regular expression for the empty set, and we denote it with the epsilon. Okay, here. Now there's a difference between epsilon and lambda. Lambda is a string, empty string. Epsilon is a regular expression which will actually denote that set containing the empty string. Oh, actually we had it here. This set. Okay, so. Here, can you see the set here? The set containing the empty string. That's what is denoted by this epsilon in the regular expression. Okay, so we do need ability to create empty strings and so on, and that's why epsilon is the regular expression for that. Okay, and the inductive part of the definition says that if R and S are 2 regular expressions, then you can combine them in 3 manners, 3 different ways, to produce a bigger regular expression. Okay, and actually those 3 ways of combining correspond to the 3 operations we looked here. Okay, so one is RS. Okay, we don't put the dot here in the operator on languages, L1 dot L2 we put the dot, but in a regular expression we just place them next to each other. We don't put the dot. Okay, RS, and I have put parentheses, but we're going to ignore the parentheses in a minute, okay? But parentheses with R and S inside that would be a new regular expression made out of 2 other regular expressions, R and S, okay? Similarly, the R plus S and also the R star, okay? So these are the 3 ways you can make new regular expressions out of existing regular expressions, okay? RS is called the concatenation, R plus S is called the union, and R star is called the Kleene closure. It is named Kleene closure, named after the person who invented it. Okay. All right. Like I said, we are going to ignore the parentheses. The parentheses may be left out, with the understanding that star operator has the highest precedence. Okay. So the star has the highest precedence. The plus operator has the next. The concatenation operation has the next precedence, the RS, and the plus has the lowest precedence. Okay, So there are three operators here, the concatenation, the plus, and the star, and these are arranged in three levels of precedence, okay? Very much like the multiplication, addition, and I guess the third one was exponentiation in mathematics, very much like that, okay? So star is the highest, concatenation is next, and then the plus is the lowest, okay? So if you understand these three levels of precedence, then we can ignore the parentheses. We don't have to ignore the parentheses, but we can if you want to, okay? To make the expression look a little bit more compact without too much of parentheses, okay? All right, so here are some examples, and these three examples I'm going to use in the rest of the slides or rest of the discussion here. So let's quickly look at these three. R1 is the regular expression AB, and then followed by A plus B star, followed by AB, okay? So that's a pretty long expression, and it does include the concatenation, the plus, and the star, okay? All three of them, okay? You can see that the plus is used here, inside here, okay? A plus B, okay? And then the star is used on A plus B, okay? The star applies to the A plus B. Now you don't see the dot operator because we don't put a dot between two, but technically between this A and this B there's a dot, okay, or there's a concatenation, okay, and between B and then this whole A plus B star there's a concatenation, okay. So this whole term which I have highlighted is a concatenation of B and A plus B star, okay, and then A plus B star is concatenated to A, and the A is concatenated to B, okay. So when you just write regular expression next to each other, there is a concatenation operation happening there, okay. So that's an example. This is the next example, A plus B star. Actually, this happens to be part of R1, okay? And the third one is AA plus BB, okay? All right, so these are the three examples we're going to use. Now, informally, actually, before we get to the what these stand for, let's define one more notion or definition, okay? Now, each of these regular expressions, which we these three examples, but you can make any number of regular expressions. Each regular expression denotes or represents a language, okay? Language means a string, a set of strings from the alphabet A, okay? And the language is defined as follows, okay? Pretty intuitive, and it's based on those these three operators here, okay? On languages. So the language for the regular expression, which is just the A, which is the alphabet symbol. Remember, I mentioned alphabet symbol by itself becomes a regular expression. And the language for that regular expression is just the set containing one string or one word, and that word has just the letter A in it, okay? So this is a single string, single letter language, okay? So that's what the A regular expression denotes. The epsilon regular expression denotes this. I already mentioned this before, okay? It denotes the set containing the empty string, okay? And then the three RS, R plus S, and R star denote the concatenation of L of R with L of S, okay? And the plus of L of R with L of S, and the star of L of R, okay? So these are inductive definitions which go ahead and apply those three operations on languages, okay? These three operations, the product, union, and star, on the languages L of R, L of S, L of R, L of S, and L of R, okay? So we apply the product of L of R and L of S, and the union of L of R and L of S, and the star operator of L of R, okay? So this very intuitive, and it matches the three operations on languages, okay? Now, suppose we take these three examples, okay? Those three examples, and they're repeated here. And we want to apply this definition to find out what language this particular regular expression denotes, or what language this particular expression denotes, and so on, okay? And what does this denote, okay? Now, maybe the third one we can knock it off quickly. This regular expression is AA plus BB. And if you apply this definition, these five definitions to that, you will notice that it will be the set, which is the union of the set obtained for AA and the set obtained for BB, okay? And the set obtained for AA will be the product of the set obtained for A with the set obtained for A, okay? and we know that the language for A is that. Okay, so when you take this one and product of this with itself, you'll get two A's. Okay, one set A, a product, another set A. Okay, if this is not very clear, let me open a quick notepad here, and yep. So basically, we are saying that the language, yep, A. Okay, so this is one set times, okay, or the dot, another, okay, another the same one, okay, L of A, okay. What would this be? So this will be the concatenation of all the strings, one string from the first language and one from the second language, okay, and that would give you the two A's, okay. So that's how we get this this language here, or this string here in this language, AA. And similarly for BB, we will get the BB, and those are the only two strings you can make. Okay, you cannot make anything else. Okay, so it's a finite language, and it's quite obvious AA plus BB what it denotes. Okay, it denotes all the strings in AA and then all the strings in BB. Okay, and the strings in AA are just the AA, one string, and the BB also is just the one string. Okay. Now this one here is called the universal language, A plus B star, and it denotes the set of all strings made up of any number of A's and any number of B's in any order, okay, including the empty string. So this really is a universal set, all strings you can make out of A's and B's, okay. So if you want to enumerate these guys, there is a standard way to do that, okay. So this A union B star, L of A plus B star, okay, yeah, L of A plus B, I probably need one more parenthesis here. L of A plus B star would be all strings, okay, including the empty string, okay. So I don't know how to put lambda here, I'll just say lambda, okay, lambda, but that's the empty string, okay. And then the A, and then the B, then AA, AB, BA, and BB, okay, and then three A's, AAB, ABA, ABB, okay. I'm not sure if you're following, but these are all the very standard way of enumerating all strings, okay. And so let me put dot 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 here. So what you do is you take all strings of length 1 and enumerate them, okay, and those are the only two. Then all strings of length 2, you enumerate them in a very systematic order, okay. This is exactly how you will enumerate the binary numbers, binary 0, 1, 2, 3, 4 in binary, okay. So A is 0 and B is 1. So if you think of that, then this is how you'll enumerate them, okay. So this is an important language for us to remember, A plus B star, okay. It's called the universal language, okay, universal language. Okay. Set of all strings made up of A's and B's in any order, including the empty string. Okay, this lambda is the empty string there. Okay. Let's look at the first one. Okay, the first one does contain the universal language in the middle. Okay, but it does contain two pieces, one piece before and one piece after. Okay, and those two pieces will force certain letters in the beginning of the strings and certain letters in the end of the string. In particular, it will force a AB in the front of the string and then AB at the end of the string. Okay. And in between, you can have anything, okay? Because A plus B star is a universal language, you can have anything, including the empty string, okay, in between, okay? And that's what is described here. So this language for AB, A plus B star AB, is the set of words W or strings W, such that W starts with an AB and ends with the AB. That's all, okay? That's an English description of that language. Now, obviously, this is an infinite language because you have A plus B star. Anytime you have the star, you would get an infinite language. Okay, so you can write many examples of words. So, for example, I can write a few words here. AB, that's the smallest one you can create. Okay, where you don't have anything in between the AB and the AB. Then AB. Of course, go ahead and put the AB at the end, and in between you can put anything you want, okay? AB, A, B, something like that. And obviously you don't put the blanks, put them all together. So that would be a word in that, because it begins with the AB, it ends with the AB. That's the only criteria, okay? It doesn't matter what's in between, okay? And so on. All right, so those are the kind of words described by this regular expression, AB, A plus B star, AB, okay? All right, so there is an intuitive language associated with every regular expression. So that's the key thing in your mind, okay? All right, so I think we have actually completed the definition of regular expressions and what they stand for and what language they denote, okay? And we have those three operations of the product and the union and then the star, Kleene star, okay? And you can make all kinds of regular expressions out of these, out of the definition there, okay? Okay, now we're going to get to the second topic here, okay? Now, what good is a regular expression if you can't implement it, right? Regular expressions is a theoretical mathematical concept, but eventually in the PLY system, in the Lexer component, okay, we specify a regular expression and automatically a Python program is generated which actually recognizes the tokens for these regular expressions, right? In the input, like car, cutter, and some of the other things like number, okay, a string of digits and so on. So those things the Lexer program recognizes. So now the question is, we want to study how does the PLY system generate that Python program which recognizes the tokens, okay? And for that, we need to understand the concept of a deterministic finite automata, okay, DFA. So let's quickly see what this is, okay? Again, it's a mathematical concept, but actually this concept, the DFA, it's called the DFA. The DFA concept is a little bit more closer to programming or program compared to the regular expression. Okay, the regular expression is a little bit more mathematical in its definition and what it denotes. Okay, but the deterministic finite automata, for all practical purposes, it looks like a computer program. Okay, but it's not. It's a mathematical definition, but it looks more like a computer program. Okay, to recognize tokens. Okay, so this is the program which the PLY system generates. Okay. So if you keep that in mind, then your understanding will be simple here, okay? So what is a deterministic finite automata? It is a mathematical model of a simple computational device, okay, that reads a string of symbols from the input alphabet A, okay? So this DFA reads an input, okay? And that input is any string, okay? From the alphabet, okay, sigma is always given to us, okay, so any string or any word it reads, and then the DFA, what it does is that it accepts or rejects that input, okay, got it? So that's the only purpose of this DFA, okay. A DFA is sometimes referred to as a language recognizer, okay, that is some strings are fed as strings are fed as input, and some of them it recognizes and says, yeah, I accept it, and others it'll reject, okay, saying, oh, I don't accept this one, okay. So that's the nature of a DFA computational model or computational device, okay. And the set of strings which are accepted by the DFA is referred to as the language of the DFA, okay. Very much like we define the language of a regular expression, we also denote the language of a DFA to be the set of strings which it accepts, okay. Now let's see what it is, okay. What is this device or what is this DFA, okay. Very much like the grammars NTPS, remember that, the four components of a grammar. The DFA also has four components, QTSF, okay. A Q is a finite set of states, okay. Any name, they can have some names, 1, 2, 3, 4, 5, or Q1, Q2, Q3. You can give any names to the states, okay. And of these states, exactly one of them is designated as the start state. Very much like in the grammars, we had the start symbol, we have a start state in DFAs, okay. And we have a subset of the states designated as final states, okay. So you can actually have more than one final state, okay. That's why we say it's a subset of Q, okay. F is the set of final states, S is a single start state, okay, and Q is the set of all states, okay. So these are all the states, and then there is an important function called the transition function. What it does is that it maps Q cross sigma to Q, okay. What this means is that it takes a state Q from the first Q, okay, it takes a state and takes a symbol from the sigma, like a A or a B, and it maps that combination of a particular state and a particular symbol into another state, okay, Q. So that's the output, okay. So the input of this function is a pair, okay, Q comma A, okay, and the output is a Q, okay, or another state Q, okay. And what is the significance of this is that because we already said that the DFA reads a string and accepts or rejects it, right? So this transition function is the methodology or the mechanism which is used to decide whether to accept or not, okay, accept the string or not, okay. And what it does is that it transitions. We'll see the example a bit later, okay. It'll become more clearer, but in general, it allows you to read a symbol from the input, and you'll always have a current state, okay. You're in the current state, and then you read the symbol, and based on the symbol, you consult this transition function and decide which state to move to, okay. So the DFA keeps on moving from one state to another state depending on the input, okay. And once the input is exhausted, we reach a state, and if that state is a final state, then we accept the string. And if it's not a final state, we reject the string. Okay, so this transition function is the mechanism used to decide whether to accept or reject. Okay, all right. So that's what a DFA is. Now, the DFA can also be pictured as a graph. This is important because pictures are easier to understand than a mathematical definition like that. Okay, and the graph contains the states as the nodes. Okay, each state becomes a node in the graph, and we're going to see some examples of this. And transitions, the transition function can be encoded as a directed edge from one node to another node, okay? Because node is a state, so it'll be an edge from one state to another state. And if you can label the edge with a symbol from the alphabet, then it becomes the one entry in the transition table, okay? Got it? So that's why we can actually nicely picture this as a graph, okay? And of course, the start state is designated by an arrow mark, okay, which comes into that state, and the final states are designated by double circles. Okay, so we're going to see some pictures here, and I'll explain this one more time. And here are the so it's time to look at the graphs. Okay, and we here in this picture, all three regular expressions are shown. Okay, the first one is AB, A plus B star, AB here on the top. Then the lower left corner is the A plus B star, and A plus BB on this side, okay? So there are these three regular expressions, and what we have shown here is a deterministic finite automata in the form of a graph, okay? And the circles here are the states, okay? The nodes, okay? The 1, the 2, the 3, the 4, the 5, and the 6. Those are the states of this DFA. Similarly, in the next DFA, this is another DFA which has only one state, okay? Small, it's a small, tiny DFA. And there's a third DFA here, which has got 1, 2, 3, 4, 5, 6 states. Oh, actually, both the first and the third have 6 states. Interesting. It's a coincidence, but that's how you denote the states in a DFA, in a graphical notation, okay? And the arrows are the transitions, okay? So an arrow from 1 to 2 labeled A indicates that there is a transition, okay? So if I want, I can, so for example, the first DFA, I can say the transition going from 1 on A, okay, equals 2, okay? Transition on state 1 on the symbol B equals 5, okay? And so on, okay? So you can actually see that the arrow from 1 to 2 labeled A is nothing but the transition function on 1 and A, okay? And 2 is given to us, okay? So that's, now of course we have to learn how to build these DFAs, okay? Actually in this class we probably won't learn how to build DFAs, but we probably are going to learn an algorithm which converts a regular expression to a DFA, okay? Anyway, the graphical notation is essentially the DFA with the starts. Oh, you can see the start state has an arrow coming in, and the final states have the double circles in them. Okay, so 6 is a final state here, 1 is a final state in this DFA, and 4 and 5 are the final states in this DFA. Okay, and 1 happens to be the start state in all of them. Okay, in all the three. Okay, so we have the start states which have an arrow coming in. In the beginning without a node to the left of it. The final states are the double circles, okay? The double circles, those are the final states, and the transitions are the edges, okay? And you can notice there are some edges which are going from 3 to 3. These are called the loops or the self edge it's called, okay? So you can have such transitions, okay? So there are quite a few of those. You can see 1, 2, 3, 4. And sometimes when there are two transitions on both A and B back to itself, we actually put a comma, okay? So this comma is really a shortcut for two different arrows going, starting from 1 and going back to 1, okay? One labeled A and one labeled B, okay? So that's just a short notation, okay? All right, maybe a few more minutes before I stop recording this video, and then we will go to the next video. I just wanted to sort of explain how I came up with this diagram, okay, or this the DFA design, okay. Let's look at the third one. I'll explain that, and then maybe we can discuss the other two later on in the next video, okay. So this one, if you recall, AA plus BB, that's a regular expression which denotes the language. Did I write that here? No, I can write it here. It denotes this language, AA comma BB, right? So it denotes this language. Only two strings, okay? So let's see how we can design a DFA which will accept only those two strings and reject everything else, okay? Exactly those two strings it must accept, okay? You always start at the start state, so you always put an arrow, put a circle, and put a 1, and that's how you start designing a DFA, okay? So you can see that that's always there in all the three DFAs, okay? Then what you do is you decide where to go on the input symbols A and B, okay? So remember, this must be in your mind that we want to accept these two strings A and BB, okay? So if in the state 1 you see the symbol A in the input, okay? First symbol you see is an A, then we transition to state 2, okay? And we sort of remember here that, oh, we have already seen one A before, okay? Same thing, if you see a B, then we transition to state 3, okay? So what has happened here in the first three states, in 1, 2, and 3, is that we start in the start state 1, and if the first symbol in the input is A, the DFA transitions to state 2, and if the first symbol is a B, then the DFA transitions to state 3, okay? Then we again try to decide what happens when you see another A or a B in state 2, and also similarly for state 3. So in state 2, if we see another A, that means we have seen two A's in a row, right? A from 1 to 2, and then another A from 2 to 4, okay? And that's the reason why we go to a state 4, and that we designate as a final state, because AA is a word which we must accept, right? So we accept it here, okay? Similarly, on the BB, you can see that it reaches the 5, okay? And 5 also is an accepting or a final state, okay? Now, on 2, you have to consider what happens if you read a B, okay? So if you saw an A first and then a B, then we know that, oh, this is not a word in the language, no matter what comes after this, right? So we reach state 6, okay? Similarly, on a B followed by A, we also reach state 6 because we have messed up, okay? And then in 6, you can see that no matter what you see, whether you see an A or a B after that, we stay in state 6, okay? That's what this loop is for, okay? So if you start with the AB, then we're going to reject it, no matter what we see after the AB, okay? So we're going to reject everything which begins with an AB, okay? In state 6, okay? Because you keep on doing this until no more input, and then you stay in the state 6. Similarly, BA, anything which starts with the BA, we reach state 6, and we reject it there, okay? The reason 6 is a reject state is because there's no way out of it. You can see that all the arrows are coming in, okay? There's no way out of 6, okay? So this sometimes we refer to as a sink state, okay? Sink state, okay? That's a state which we reject every word, okay? Now, if you do reach 4 or 5, okay, 4 you reach with the AA, and 5 you reach with the BB. Now, after that, we should not see any symbols, okay? But if you do see a symbol after the two A's, then also we have to reject those words, right? So that's why we send AB transitions, both the transitions into 6 from 4 as well as 5, okay? So now, and that completes the diagram, okay? That completes all the transitions, and you can actually see that if you follow the rule that you start from state 1 and then keep moving from one state to another state by following the input symbols one after the other, and once the input is exhausted, then if you are in state 4 or 5, you would accept, and in particular, you'll accept the AA and the BB, and then otherwise you'll reject, okay? If you end up in any one of the other states like 1, 2, 3, or 6, at the end, after exhausting the whole input, then you would reject this, okay? So I think you should get a good feel for this particular DFA, which I just explained. And this DFA has 6 states, and it accepts this language, AABB language, okay? And which is the language denoted by this regular expression here, AA plus BB, okay? Okay, I'm going to stop recording here because I don't like long recording. So I'll go to part 2 and then continue with these slides and see you in a bit, okay?